from knowledge to action as an excellent strategy to finally deal with climate change. I work at Munich RE, and I would like to give you an insight, or to provide insight at how Munich RE prepares for future changes and future challenges, how we obtain knowledge and how we put it into action. Munich RE was founded in 1880, and it's today one of the leading global reinsurance companies. Covering risk of natural hazards is an essential part of our business. We advise customers with peak risks of different natural hazards in many markets worldwide, because our business model builds on diversification of those risks. The global diversification of risks is an essential part, and it's achieved in two ways. On the one hand, by addressing different markets, such as Japan or Europe, and on the other hand, by addressing different risks, ideally independent, for example, such as earthquakes or winter storms. This shows pretty well at looking at last year's example, last year's event. We observed a global distribution of the relevant natural catastrophe loss events. They range from earthquakes in Japan in June, or from winter storms in Europe, the winter storm Friederike in January. We had hurricanes in the USA, like Florence or Michael. And in addition to those geophysical events and meteorological events, we also observed climatological events, such as wildfires in the USA, like the Camp Fire or the Woolsey Fire, or droughts in Europe. It is important for us to know how these risks, first of all, to know these risks in detail, and to know how these risks change with respect to climate change. The relevant natural hazards or the relevant events are tracked in our NatCat service database. The database goes back to 1980 for all relevant events. For USA and Europe, even until 1970. And we even have 3,000 historical events since 79 Anno Domini. Currently, there are more than 37,000 data sets. And this tool is an important, this NatCat service is an important tool for risk analysis and also for research with respect to changes with climate. Interestingly, Munich RE was the first alerter in industry to climate change. Already in 1979, Munich RE pointed out the effects of rising temperatures of Earth's atmosphere as a result with glaciers and polar caps receding, surface lakes reducing, and ocean temperatures rising. In addition, they pointed out the rise of the CO2 content of the air, causing a change in the absorption of solar energy. And therefore, Munich RE has a long tradition, more than 40 years, where they analyzed changes and the impacts of risks. This long tradition is not only in publishing in-house journals such as the flood inundation, as you see on the screen, but also more recently geotopic journals, but also by publishing in peer-reviewed journals. Beyond the regular research that is done at Munich RE, colleagues have also contributed to the well-known IPCC report. For example, 2001, Dr. Gerhard Berz has been lead author to the chapter Insurance and Other Financial Services. And in 2013 and 14, Dr. Eberhard Faust has been lead author of the chapter Key Economic Sectors and Services, both of the Working Group 2 of Impacts, Adaptation and Vulnerability. This long tradition of scientific research projects ranges with cooperations with different partners. We have cooperations between universities or scientific institutes. There are European and German projects where we are involved, and many of them deal with the analysis of the natural hazards and especially their related risks and changes. I would like to focus on severe convective storms, so the risks of thunderstorms and their hazards such as hail or tornadoes or one of those research projects that Munich RE was involved in was a couple of years ago, where they analyzed changes in thunderstorm-related losses in the USA. They found a trend in the losses, and this trend is reflected in the meteorological forcings. That means that in this study, the colleagues, also Eberhard Faust was involved in it, and was a cooperation with the German Aerospace Center in Oberpfaffenhofen. They found that climatological changes are driving thunderstorm-related losses, and that's a very important finding. It is explainable by changes or by other studies, which looked at changes in surface humidity or the low-level specific humidity. For example, a study by Willett et al. In 2013, they found trends in the surface humidity which affects thunderstorm development and severity. These were studies obtained for the USA. We have also the most recent research project where we were active in was the ARCS project. ARCS stands for Analysis of Changes in the Risk of Severe Convective Storms in Europe. And it was a cooperation between Munich RE and the European Severe Storms Laboratory, the ESSL. It was funded by the Federal Ministry of Education and Research, so it was a German project, and also cooperation with the German Aerospace Center. Within this project, we focused on Europe. We wanted to increase the knowledge about these natural hazards that are coming from thunderstorm-driven hazards. We also wanted to detect whether there are already past trends or future trends. We wanted to see changes in the variability and especially how they relate with climate change, the trends. An important part, as we're a reinsurance company, is not only to have a look at the hazards, but also to have a translation between these analyses we found in hazards into the risk. Because risk is not only depending on the hazards, a risk is also depending on the exposure. So for example, a house that's possibly under effect of a hailstorm, and as another factor in the function of our risk is the vulnerability. So how vulnerable are these exposures which are affected? The first part is the hazard part, which is the one where we focus to work with different the research institutes. The difficulty of dealing with thunderstorm-related losses is that thunderstorms are very local and small-scale phenomenon. They cannot be resolved by climate models, or they can also not be resolved by reanalysis, which are available for the past 40 years. Therefore, we first had to develop a statistical model which takes into account atmospheric conditions to link them to the occurrence of thunderstorms and their related hazards. Using the statistical models, it was possible to look at the past climate by applying it to the area interim reanalysis, but also to apply it to future climate scenarios, for example, from Eurocordix, where both of these simulations have a temporal resolution of 6 hours and spatial resolutions of 40, 50 to 80 kilometers, which is of course too coarse to deal with thunderstorms. And that's why we needed the link with the statistical model. To show you the results of what we found for the past climate, we found that for hail larger than 2 centimeters, it mostly occurs within northern Italy, along the Adriatic coast, and there's a strong gradient within Germany from south to north. When looking at the trend on the right side, we already detected a trend in the last 40 years, or 39 years, with almost increases everywhere throughout the domain, especially in these areas where there was already a high frequency. Decreases were only found for Spain or for France. the dots are also indicating significant changes. So we already see significant changes in frequency and hazard frequency in the past. There have also been studies, for example, from Michael Kunz, who found that there's an increase in the hail loss days within the last decades in the southwest of Germany, which is exactly in this domain. When we wanted to know what we have to expect in the future, especially with climate change, we took 14 regional climate models into account. We used different greenhouse emission scenarios, for example, the RCP 4.5 and the RCP 8.5, which means that we have the radiative forcing after the 21st century at 4.5 watt per square meters and 8.5, which is the business as usual scenario. And for hail 2 centimeter, we found a drastic increase in the occurrence of these events, depending the intensity or the increase depends on the scenario and also on the time period. When we look at the business as usual scenario and the end of the century, which is on the right, we saw an increase of more than 80% in Central Europe and Eastern Europe in the frequency of large hail events. When we look at even more severe events, such as hail 5 centimeter, which have the potential to damage for even larger damage and to destroy even more values, the increase was even larger that we found. In the business as usual, well over 160% in some areas. So being tackled with changes on the hazard side as a reinsurance, of course, we need to know how does this affects the risk itself, because hazard is not the only component. So that's why we use risk models in order to learn about the costs of these hazards. The first approach is to generate a large event set where we have multiple events and where we can estimate how much would a 1,000-year event cost. For our study, we were happy to receive high-resolution radar data from the DWD, where we could identify hail tracks within Germany. So you see here a product, the vertical integrated ice from the DWD, and these black ellipses are the identified hail tracks or hail ellipses, and on the small triangles are the observations that we are also happy to use or also to compare it. So the goal is to, or the aim is to have an event set. If we combine the event set, or if we have the event set, then we can come up with a possible event. We can combine it with exposure, what it hits. We can combine it with vulnerabilities, how vulnerable the exposure is, and that's how we obtain the risk. So to come back to this function. One part, let's start with the first part. The first part is to simulate these hail swaths. To simulate these hail swaths, we use the observed local hail tracks. We obtained the area that's affected, the angle of these ellipsoids, and we obtained using observations also the distribution of the hail size within these hailstorms, which is, of course, very difficult. That's why we also needed to take into account reanalysis data in order to have an insight in the atmospheric conditions. Using these hail tracks, we got many distributions where we can draw from to create a artificial hail, as for example this one. So this has a specific area that's affected. In this case, it's a quite large area, but you might recognize it from June this year, which was the hailstorm that affected Munich. There is a distribution of the hail size within this hail track, and that's our simulated hazard. In addition, we need to compute the expected loss by applying our formula, by getting hint of the exposure, as we are a research, or as we were working with within a research project, we used openly available data, such as the CAPRA dataset, which is the image here in the middle, which gives you the exposure, in this case, the residential, commercial, and industrial exposure, so all possible exposure for one grid point from the CAPRA dataset. And we developed this vulnerability curve, which shows you how much loss, or how the loss ratio depends on the hail size diameter. Using those three components, we can predict the total loss of this special event, or of this single hail event. This loss is now in euros, so we translated hazard, hail sizes, into the damage that they cost. If we repeat this simulation of hail swath, vulnerability curve, exposure, and risk modeling, for example, 100 times for the past, we can get a hint on the range of possible losses. And we can also apply it on different climatological simulations in order to just change the hazard component to see how the risk will change if we have, for example, a lot more large hail or other severe hazards. These are some results that I would like to show you. They're preliminary results since the project is still going on, but I think they will give you a hint in how difficult it is to deal with simulations of losses and compare them to observations. We have 100 realizations of these annual losses from ERA interim, so we use the reanalysis since 1979. And in this case, we also compared it to the data which is in the NatCat service database, so the loss data that we collected in our database for the same time period. It is hard to compare both data because for the hail, we only simulated hail-only events and hail-only losses, but for observed losses, we never get the amount of what is the effect of wind, what is the effect of water, or what is the effect of hail. We can never distinguish between those effects, so we just get a number and we have to deal with comparing or trying to estimate the single parts of it. When we have these 100 realizations of these annual losses, we can then create such a PML curve, which is the probable maximum loss, which pretty much tells you what would a 10-year event cost, or what would a 1,000-year event cost using these 100 realizations. These PML curves, of course, 100 realizations are not enough to get a 1,000-year event. That's, I think, clear to everyone. So that's why we need to get a really large event set and to simulate 100,000 of year in order to get a stable estimation of the cost of a 1,000-year event. So now, what happens if we have a change in the hazard which increases these losses? That would mean that the 10-year event, or the cost for a 10-year event, could probably occur every 5 years, or the 10-year event would be double as high as before. So that are very important questions to know, because the business model, or the business model of Munich RE does only hold if we know the risks and we also know how they will change. To conclude my talk, I would like to emphasize that with projects like the NatCat service database, different scientific studies and publications in different research institutes, projects with partners from universities and publications, we try to increase our knowledge continuously and to continue the long tradition on the close connection between the industry and the research. We put this knowledge into action by giving advice to our customers, advise them about their risks, about their changes of the risks, and also taking into account the obtained knowledge into our risk modeling.